One of you asked me, why is the fundamental theorem of arithmetic a big deal? Why is it fundamental? And why is it even something that we need to prove? The fundamental theorem of arithmetic being the statement that every natural number has a unique factorization into prime numbers. So it's unique. And that's some very intuitive statement to us because we are used to small numbers like 12 and 25 and so on where this happens. But why couldn't there be a very large natural number that has two distinct prime factorizations? That is p times q, but it's also r times s, where p, q, r, and s are primes. Why can't that happen? Maybe very far down the number line, there is a coincidence like that. Why couldn't it happen? And of course, the point is that we can prove that it cannot happen for the natural numbers. But there are other number systems, like the natural numbers, where it does happen. For example, think of the even numbers. So now our number system now is just the even numbers, and the primes in this system are even numbers that cannot be factored into other even numbers. So for example, 2 is an even number that is a prime here. 4 is an even number that is not prime because it's 2 times 2, but 6 is a prime number because it cannot be factored as the product of two even numbers. And now consider 6 times 10. 6 is a prime, 10 is a prime, so that is a prime factorization of the number 60, but 60 can also be factored as 2 times 30. But 2 and 30 are also primes, so 60 has two different prime factorizations. And that is just one example, but there are other examples that are perhaps even more natural, which are rings of integers of other what we call number fields. So for example, the integers adjoin I, that is the ring of integers of Q adjoin I, and those work and behave exactly like the integers, but in some of those ring of integers we have unique factorization, and in some other ones we do not. And since there are interesting examples of integer rings where this doesn't happen, then it's very important to study when does it happen and why does it happen for the integers themselves. As a side note, there is a very important, a very famous wrong proof of Fermat's last theorem by Lamé that actually relied on him assuming that some other ring of integers had unique factorization, but they do not. And actually that wrong proof of Fermat's last theorem started the systematic study of these number fields and of these ring of integers where there is not unique factorization.